Okay. Well, I will start from the point I left yesterday. I was describing the replica trick to compute the entanglement entropy with the path integral directly in the continuum. So the idea was first we have the vacuum wave functional. Put this. Vacuum wave functional that is given by a path integral over half Euclidean space, with some boundary condition at time zero, that is this function of the coordinates, that is just the variable where we evaluate the wave function. And then with this, we can produce the density matrix of a region V, here an interval in 2 dimensions. This is an interval in 2 dimensions, and then this has 2 boundaries. The 2 boundaries are the entries of the density matrix. And this is given by the path integral with the specific boundary conditions on the cut, in the path integral over the whole Euclidean plane. And now we want to compute the entropy out of this density matrix. For that, instead of computing directly the entropy that contains this logarithm, we first compute this quantity that are traces of integer powers of the density matrix. And I showed you an example. We have here the computation of trace of rho to the 3rd power, and you produce then 3 copies of the density matrix that are these 3 copies of the Euclidean plane with a cut, and then so one of the boundaries, let's say the output variable of one of the density matrix with the input variable of the other, and do the same for the second density matrix, and the last one you identify the boundaries because of the trace. And then at the end, you don't have any boundaries, so the path integral over this manifold is just a number that is the trace of rho to the cube. So the path integral is over a n-sheeted manifold, where n is the power of the density matrix, which has some identifications along the cut over the region B. The first thing on this geometry is that there is no cut. There is no real cut. In the geometry, I show you that if you are in a point here, you move around this point and you will find that there is like a normal Euclidean plane around it. But there are conical singularities at the boundary of the region, which have an angle 2 pi n. So this gives you the computation of traces of rho to the n, and then we can write it as traces of rho to the n equal to the partition function on an n-replicating manifold divided the partition function in the Euclidean plane to the power n. This is just a normalization, because here this n here is the normalization of the density matrix just to have trace 1. This is just a partition function for one sheet in the Euclidean plane without any cut. So if you produce powers of the density matrix, we'll have powers of this normalization. And from here, we can compute a quantity that is, well, these are the traces of rho to the n, but it's better to express this in terms of the so-called range entropies. Which are just basically the logarithm, except for a constant, is the logarithm of the traces of rho to the n. which have this expression in terms of path integrals. These are kind of entropic quantities because there is this logarithm here that ensures that if you have a separated independent systems, it will add these range entropies, but in general they don't have many interesting properties as the usual von Neumann entropy has. But still, if you compute these quantities, they behave very similarly to the entanglement entropy. For example, they have the same type of structure of singularities, etc. And in particular, they are useful because the limit when n goes to 1 is just the von Neumann entropy. So then the idea of the replica trick, if you want to compute the entropy, you can also compute the range entropies that are interesting in some sense. But if you want to compute the entropy, is just compute the range entropies for integer n, and then do the analytic continuation for n real and go to n equal to 1, and this gives you the entropy. Sometimes it can be done, sometimes it's difficult and you don't know how to do it, but in general, this is the procedure. Let me remark two things. The path integral formulation only works for any integer. Except in some particular situation when there are some special symmetries, you can continue in the geometry in n in those cases, but in general you cannot. And the second important point of this replica trick is that it shows you that there is a completely geometrical prescription that is valid for any theory, right? You have just to evaluate the partition function in a specific geometry, and this is related to the holographic entanglement entropy, which somehow in the holographic theories, this prescription, this geometric prescription for the range entropies is better used in the sense that at the end you get a geometric prescription also for the entropy. Well, these range entropies that are just a rewriting of the traces for rho to the n, they do not have many interesting properties from the information theory point of view, but still they are very interesting from the quantum point of view because they are related to operators. These are called twist operators. And the idea is that the traces of rho to the n for integer powers are in fact vacuum expectation values or expectation values in the state you are looking at of some operators, where here I put in this n, meaning that is in the replicated theory. So as they are particular expectation values of operators, they enjoy the properties of expectation values of operators, and then there are many things you can do with that. What are these operators? These are called, in this particular case, I will call it range twist operators. And the idea is that if you have the quantum field theory, you can automatically construct another theory that is the quantum field theory to the power n, just putting n copies of the original quantum field theory independent to each other is a silly thing to do. But then you see that this theory has a symmetry that is just the group of permutations, permutations of the n copies. And it's a global symmetry. And once you have a global symmetry, you have always these twist operators. For any of the operations of the symmetry or any of the global of the elements of the group, you have these twist operators. What are these twist operators? Are just operators that implement the symmetry only in a region of the space, just in a region of the space. For example, here we will implement the operation only here, and this operation in this case is an operation that permutes between these different copies in a cyclic way. So in the particular operators, twist operators in the range operators are cyclic symmetry operators. Restricted to some region B. But it can be done for any global symmetry. I will regain this subject again in the last lecture. And one could think, well, this stuff of the range twist operators it only happens for quantum field theories, but it's not true. It can also be done for any finite system. It also holds for finite systems. Suppose you have some system with some partition V times V prime over Hilbert space. So you have a Hilbert space of, I'm calling here with a region and the complement, but it's just a partition, a bipartite system. And then you can produce the n replicated system and the replicated original state or vacuum state or whatever state you want, which is just a tensor product of the different vacuum state for each copy. So, and then you have a Hilbert space for each of the copies, which is a tensor product too. And then you can choose a particular basis for the Hilbert spaces for this tensor product. And then you can see that the twist operator in B will be written like the product over the copies over this, of a sum over the basis of the element of the basis. These are the elements of the basis in the region B times the identity in B prime. And it's a simple computation. You can compute the expectation values of these operators, and it will give you the trace of rho to the n of the trace of the density matrix in the original copy, which has the region B to the power n. So it's a very general thing. And somehow it allows you to relate entropic quantities to something that is measurable, because it's an operator. Somehow you can, in principle, think in measuring operators related to the twist. Well, there is a question of this. Well, I will give you an example of this, the simplest example of calculation of the density matrix in a quantum field theory is the case of a Rindler wedge. This is just the region of Minkowski space given by x1 greater than the absolute value x0. So we have this region, this wedge here, that corresponds at t equal to 0 to this half plane. So when we do the replica trick, or we do the path integral formulation in Euclidean time of the density matrix corresponding to half a space, what we get is a cut going to infinity without two boundaries. And then there is a symmetry in this space, that is a symmetry of rotations here. And you can see that the density matrix, which is a function of the two boundary conditions here and here, will be given by the rotation operator of 2 pi evaluated between the two boundary states. So we have a prescription for the density matrix operator here, that in Euclidean space is a rotation of angle 2 pi, just simply that. When you go to real time, this gives that the density matrix is the exponential, so the rotation of a finite angle will be the exponential of the angle times the generator. And when you go to real time, this generator corresponds to the boost operator. So K is equal to 2 pi. This remembers the angle 2 pi in the Euclidean formulation times the boost operator. In fact, it's half the boost operator. So I'm here writing the boost operator as an integral of the nether current, corresponding nether current. So this is half of the boost operator. And this gives us exactly the value of the modular Hamiltonian. The modular Hamiltonian this is the modular Hamiltonian. In this case, which is very peculiar because it is local in the energy density operator. It's an integral of a local operator. In this case, it's only given by an integral of the energy density. And this is quite peculiar. It doesn't hold for non-relativistic theories, for relativistic theories with different state and the vacuum or different regions. So it holds only in this particular case, or in general cases which are related to this one by symmetries. So in this case, the modular flow, remember that the modular flow were these imaginary powers of the density matrix. So the unitary that you get from the modular flow for the modular flow are just the boost transformations. So the modular flow acts locally on operators if you have the Minkowski space. These are the boost orbits. So the modular flow moves operators along the boost orbits. And here, this operator will make the transformation on the algebra, the original algebra, the algebra of region B, which was the Rindler wedge, but it can be extended if I put here the full boost operator. Can be extended to all Minkowski space. And this particular, so we see that from the vacuum state, we get reduced to half a space, we get the boost operator. And somehow the information of the stress tensor of the theory, the energy density operator of the theory, is in the density matrix of the vacuum state. And this is related to the Unruh effect. The Unruh effect say that accelerated observers with constant acceleration see the vacuum as a thermal state of temperature T equal to acceleration over 2 pi. And we can show this very simply, because suppose that you have an accelerator observer with constant acceleration will describe one of these orbits. In fact, it's easy to show that it will describe one of these orbits where this distance is a to the minus 1, a being the acceleration. So, and it follows that along this orbit, the proper time times the acceleration is equal to the parameter of the boost orbit. So if the state is e to the minus 2 pi, the generator of boost, it will be, you can write this as e to the minus the Hamiltonian of proper time divided by acceleration times 2 pi. And from here, you can read off, this is when it multiplies to the Hamiltonian is the inverse temperature. So you can read off that temperature is A over 2 pi. And this is also related to Hawking temperature, because if you have the space-time of a black hole, and you think a state that is in equilibrium with respect to the Killing symmetry. The Killing symmetry looks like something like this here, geometrically. Moves points in this manner. Well, very near the horizon, this is approximately is proportional to the boost, and very far away is proportional to usual time for accelerate for asymptotic observers. So if you have if your black hole is in thermal equilibrium at some temperature, it means that your modular Hamiltonian here is e to the minus some beta, the usual Hamiltonian, because it's time translation. And in order that this modular Hamiltonian here has the right temperature, that is 2 pi, so here it has to be e to the minus 2 pi, the boost operator. It tells you that the black hole cannot be at thermal equilibrium unless your temperature at infinity, your beta here, is the Hawking temperature. Otherwise, it will have something here that is very different from the boost operator, and so locally you don't see here for small regions near the horizon, you don't see Minkowski space, and then it's somehow a violation of equivalent principles. Okay, this was I have finished my general introduction on these things. Now I move to an application. An application on the irreversibility of the Romanization group. With entanglement entropy. So using entanglement entropy, let's call it the entropic version. So let me first describe what is this irreversibility of the Romanization group. The Romanization group, we can think we have in this plane, we have this plane shows the coupling constants of some theory, the possible coupling constants. And then at some points of this space, you will have some CFTs. Let me call it CFT1, CFT2. And then the Romanization group describes a flow in the space of coupling constants as you move in size, in energy. So you can see that, for example, some theory will move with the Romanization group in some flow. For example, flowing from CFT1 to CFT2. This will be for short distances in the UV, and this will be for large distances in the IR, for example. And then the irreversibility Romanization group tells that if you have a situation where CFT1 goes to CFT2, it cannot happen that you have another theory that is not conformal, but there are fixed points at small scales, and larger scales are CFT2, and you go to CFT1. So this is not possible if this is true. So there is something that is lost along the Romanization group flow. We know that this is correct for dimension d equal 2, 3, and 4. This is the status up to now. What we need to prove this? So some non-perturbative inequality that is valid for any quantum field theory. And it needs to give information about the quantity that is finite and well-defined for CFTs. Because we want to understand how to say that this CFT, there must be something that is different for this CFT with respect to this one that makes the Romanization group flow in one direction and not in the other. And automatically this quantity is dimensionless because it's a well-defined quantity for a CFT. And you don't want to that the quantity has dimensions, because otherwise, as you change the size of the as you increase the size, you zoom in, for example, the quantity will change, and you don't want to do that. You want to classify the theory to give a number for the CFT. Well, there are proofs.
Excuse me.
Yes.
Just one question. With D, you mean space dimension or space-time dimension?
Space-time dimension. Space-time dimension.
Okay, thank you.
There are some previous proof not using entanglement entropy. For D equal to 2, we have some homological proof. That uses T mu nu correlators that of course can be defined for any theory, at least the ones that contain the T mu nu and stress tensor. This is in the 86. And for D equal to 4, there is Komarkovsky and Schwimmer proof that uses dilaton field effective action. In both cases, the positivity or the inequality that you use is related to Hilbert space, to the positive definite Hilbert space scalar product. So normal unitarity, let's say. And here we will use entanglement entropy, and we will use a different property. It's called Strong's relativity. But let me first describe what is the quantity that will result monotonic. For that, I will show more precisely what is expected for the entanglement entropy of spheres in a CFT. I described it yesterday, the case of D equal to 4, but in general, you expect that the entropy has some area term plus some subleading plus, and at the end, the last term will be, depending of if the dimension is even or odd, it will be -1 to the -2 over 2 for A. There is a logarithmic term in the case of dimension even, and there is a constant term for the odd. This was the case of this even case was the case I described yesterday for dimension 4. And what are these? So the reversibility theorem will be about these A and F quantities, which are dimensionless, are the last terms in the expansion of the entropy of spheres. In particular, this A is equal to the Virasoro central charge over 12 for D equal to D equal to. What are these quantities? Well, A is given by the trace anomaly. If you have a conformal field theory and you take the trace of the stress tensor, is 0. The stress tensor has 0 trace in a conformal field theory. But if you put it in a manifold with a metric different from the flat space, you get some contribution that has to have the same dimensions as the stress tensor, so it's dimension D, and it has to be constructed locally out of the curvature. So you have, in general, some expansion. Where these and these are polynomials of the curvature, so they are polynomials of D over 2 curvatures, because the R mu sigma delta has dimension 2. And this coefficient is a particular coefficient that is the one that appears here in the sphere. It's a coefficient that multiplies some particular combination of curvatures that is called the Euler anomaly, the Euler term, which integrated over the manifold gives the Euler characteristic of the manifold. It's a topological number. So these other coefficients multiplying other polynomials of the curvature do not enter into the entropy of spheres and do not enter into the irreversibility theorems. For dimension, for all, if this is even dimension, for all dimension, you have to construct the partition function on SD and a sphere, Euclidean sphere of dimension D, and then the partition function, the free energy will have an expansion here, divergent piece is non-universal, and the last term is this quantity F, is a constant term. So this I will move out. Yes. This is the constant term. So I haven't, I didn't provide a proof here. I will not do it because of time on how these same numbers appear in the expansion of the entropy of a sphere. But they are there for a good reason. So and the proof is in my notes if you want to see that. So let us see how this proof of the reversibility goes. So how much time do we have? So I started at 5. At 3,
you
right?
have, right, so you have half an hour.
Okay, perfect. So we will use 3 properties. we will use
Can I ask you a question?
yes.
So in even dimensions, it seems like you're working with the coefficients of the trace anomaly polynomial. In odd dimensions, what is the physical intuition behind using the partition function on a sphere?
Well, in fact, you can see that there is a very different thing. So this A here in the entropy itself, you can see that the A term multiplies a non-local piece and also a local piece, right? So it has the two things together. So it means that this A somehow can be obtained also from something quite local, like an anomaly. In this case, the F term is just a completely non-local quantity. So you can think there is no way to obtain this F term, this F number, using expectation values of operator correlators in an easy way. It has to, it depends really very non-locally on the whole theory. So this is the reason why one is given by an anomaly that you can obtain by expectation value of the stress tensor in a manifold, but you can also obtain the same number from the three-point function of the stress tensor, for example. So it's a quantity that you can obtain, I wouldn't say easily, but it's related to correlators. While this F thing,
you need something global for this.
It's very global and happens to appear also in the partition function so both these quantities appear in the partition function of the dimensional sphere, and the way it appears in the entropy is because you can map the sphere to the static patch in the Sitter space and then compute the entropy thermodynamically, and it happens to lead you to d-dimensional Euclidean sphere, and then this is the connection. In fact, people, Cardi, after the paper by Samologico, proposed that A was the good quantity for the reversibility theorem in any dimensions, in any even dimension, of course, because there are no trace anomalies in odd dimensions. This thing vanishes in odd dimensions because you don't have polynomials with a dimension D. You have only polynomials with dimension even. But then, well, it was Myers and Sinha that testing the Normalization Group flow in holographic theories realized that you can think this quantity was the one that was well, in fact they said that this quantity in the entropy was the one that was irreversible, and then the group by Klebanov, Kufu, Safi, and they independently proposed this number here in the partition function of a d-dimensional Euclidean sphere as the irreversible quantity. And then the two things are connected, in fact. So why is that Normalization Group flow irreversibility is connected to spheres? Well, we will see something about that in what follows. There is some connection that we can see geometrically.
Excuse me, I have a question.
Yeah.
I don't quite understand what it means to compute the entanglement entropy along an RG flow. I thought that when we go along an RG flow, that's just an effective description of the same theory at lower energies.
Yeah, very good. So the normalization group flow, as it is usually presented in this way, of in the coupling constant. So it's a flowing coupling constant is something is some like perturbative version. So there is really no such space of non-perturbative coupling constant or Lagrangian or all that is in a perturbative scheme somehow. or you have to have some scheme where you produce an action or all that. So here what we are discussing is how the theory behaves between short distances and large distances. So in our case, we'll have a very precise meaning as something that changes when you compute something, some universal quantity out of the entropy for very short or very small spheres or very large spheres. This will be the inequality that you find. But of course, it's related. It's more beyond the mathematical idea of having something non-perturbative defined somehow. There is a connection, of course, because if you move in size, some dimensionless quantity is, you can say, well, it's the same as moving my definition of all dimensionful quantities of my theory in the reverse direction. You know, you understand that?
Yes, thank you.
So we have to use, we will use three properties. One is causality, in the sense that I haven't mentioned this before, but if you have a region, so suppose you have a Cauchy surface in the Cauchy space, and you select your region B like this. Then if you have another Cauchy surface that goes like this is B prime, so the entanglement entropy of this and this will be the same, because there is a unitary evolution here that doesn't change the entropy, or you can say that you trace out from the global state the same part of the same degrees of freedom in this part of the Cauchy surface. So in fact, the entanglement entropy is not a function of a piece of a spatial surface, but is a quantity that depends on this diamond. It's a quantity that depends on the causal domain of dependence of a piece of a Cauchy surface. So it's a function of diamonds. This
Sorry,
is the
sorry.
first, yeah.
I don't think I actually understand. When you wrote down the formula for the entanglement entropy, there was a dependence on R, which is the size of the sphere, and then the A and F seem to be independent of the size of the sphere. So why would they now change when we change the size of the sphere?
Yeah, well, I've shown something like that in yesterday.
Oh, that is just for a CFT. Now we're doing it for QFTs.
Yeah, exactly. Well,
okay.
that's the point. You
Okay.
have to have a QFT that approaches some CFT for short distances and approaches another one for large distances, and then it changes it doesn't change the coefficient of the logarithmic term in the derivation. Logarithmic log epsilon will always be multiplied by A ultraviolet because it's divergent. But what changes is log R. So it's for large spheres is like this, for short spheres is like this. So you have to understand how it moves with R.
Yeah, great. Thank you.
So the second thing that we will use is an inequality that is a strong subadditivity. No, I don't know if I put many I's, but okay, it's a strong subadditivity that I think you have already seen that. If I take two regions, A and B, the strong subadditivity writes S of A plus S of B, is greater or equal that the intersection, that the entropy of the intersection which is quite a geometric thing. for these algebras of regions. It's important that you have to apply this only when these regions live in the same Cauchy surface. You cannot do take two diamonds and apply strong subjectivity. Doesn't hold. So they have to live in a, let's say, in a spatial plane or on a flat, sorry, in a spatial Cauchy surface. And the third thing that we will use is Lorentz invariance. In vacuum state. So once you accept all these three things, everything turns out to be just a geometric thing. So you have to use geometry and everything will hold. But before starting to show the Reversibility Theorem, let me first try to understand, because what are the type of regions that we need to use? Because strong subjectivity can be used for any type of regions. So one important point is that as this is the inequality that we are going to use, we must have the case that this inequality will saturate in a conformal field theory. In some particular geometric setup, it should saturate for a conformal field theory. Otherwise, we are not going to say anything interesting about the Normalization Group flow, because we want some quantity that do not move at all for a conformal field theory. So we need the saturation of this inequality. So when the first question is when strong subjectivity saturates in a conformal field theory. We not need that it saturates for any theory, but for a conformal field theory. So and then when the strong subjectivity saturates, it is called the state, and these algebras are called is a Markov state. And it has been studied in the literature by in a paper by Hayden, Josa, Petz, and Winter in 2004, that if you have saturation, let me write this. This is A and this is B. Let me call 1, 2, and 3 the three pieces in which they are divided here. When they saturate, so strong subjectivity is equal to 0. If and only if you can write the Hilbert space in the region 2 as a sum of different sectors which are in tensor product. This is like left and right. So it's just a sum of tensor products in such a way that your state, the global state in the three regions together, is a sum, some probabilities. Time density matrix is like this. So this is a Markov state. Now, if you trace,
sorry.
Yes.
Oh, I was going to ask, do you know what the intuition is for why a QFT state has to have this particular structure?
It's a good question that I'm not sure I'm able to answer well. Well, of course, in the classical case, you can see and you can compute this easily, and it turns out to be the case that so the reason, well, an important fact is that as strong subjectivity is an inequality and saturation of an inequality is always very strong. It tells you something very strong. And in this case, it somehow tell you that the relation between the region 1, sorry, here you cannot see, the region 1 and the region 3 is intermediated by the region 2. It's somehow region 1 is correlated to 2 and region 2 is correlated to 3. And because they are both correlated to 2, they are correlated to each other, but they have an intermediate in the region 2. But I cannot answer exactly why why one would expect, you know, it's difficult for me to say that. No.
So I guess, is it like all the correlations are short range, or is that the wrong way of thinking?
Well, yeah, you know, the Markov processes, the original works of Markov, were in the situation where 1, 2, and 3 are in different times, in such a way that what happens in 3 is determined by what happens in 2, and it's kind of locality in time. Here is a locality in space. What we are looking at.
Okay, thank you.
What? Yeah. Okay. Once we accept this structure, what we have is that if you trace over the region 2, you get the density matrix in 1, 3 is just a sum P sub k rho 1k times rho k 3. And so this is no, there is no quantum entanglement. Between 1 and 3. Sorry, this is again bothering me. So there is no quantum entanglement between 1 and 3. And then we have to look for some regions where there is no quantum entanglement between 1 and 3. And we usually think there is a lot of entanglement, or at least it's not a lot, but there is always entanglement in quantum field theory. Well, this can be said more precisely. In general, there is always entanglement because of Slider theorem. What this theorem tells is that if you have some region with some volume in space-time, and you apply field operators to the vacuum, so you apply phi is 1, phi xn to the vacuum, it will generate a dense set of states in the Hilbert space. So this is very counterintuitive, because acting on the vacuum in a finite region, you can generate particles or states very near particles that are very far away. And this is because of entanglement. And the way the real Slider theorem is proved is the following. Suppose that this is not the case, that this does not generate where x1 and xn are points inside the region. This does not generate a dense set of states. It must be the case then that there is some state that is orthogonal to all this. For any points inside the region. And this is 0, right? But then, because of analyticity, this implies that this quantity is 0 for all x1 in Minkowski space. So then it must be the case, because by definition the Hilbert space is generated by the field operators acting on a vacuum for all points of the space-time. So it implies that phi is just 0. So this is the way the Reversibility theorem works. And how is this related to this saturation strong relativity? Well, now suppose you have, I'm drawing now the space-time diamonds. Again, this is A, this is B, this is region 1, this is region 2 and region 3. Then I can act with an operator here and create basically any state in the Hilbert space. In particular, I can create a state that is entangled. Let's say an EPR pair between region 1 and 3. It means that acting with local operators in region 1, I can create an entangled pair. So it means that there is some disty-level entanglement. And this, of course, implies that strong relativity cannot be 0, because one of the conditions of the strong relativity is non-zero is that there is quantum entanglement. If there is no quantum entanglement between 1 and 3. I don't know if you know what is this level entanglement, but it's some particular measure of entanglement. So then strong relativity cannot be saturated in general. So what is the way out of this is to think in some particular geometric configuration where these diamonds are in such positions that the region 1 and the region 3, oh, sorry, this is 2, the region 1 and the region 3 are null surfaces. In this case, the Reversibility theorem does not work because we don't have volume. They don't have space-time volume. And then the arguments about analyticity cannot be used. In general, however, this will not give you strong relativity equal to 0. In general, it's not the case, but there are some particular case that is easy to prove that gives equal to 0. And this is the case where your regions have boundary in a null plane. So we take a null plane. This is a null plane. And I'm going to draw boundaries of regions. In the null plane. So this, let me call this gamma 1, gamma 2. For each of these boundaries, there is a region that has some space-time volume. I'm drawing here more or less the shape that it has. It's like a Rindel wedge. It's like a Rindel wedge, but the form. It's the form, the boundary of the Rindel wedge will be just a line. This will be a Rindel wedge. And here I'm drawing some other curves on the null plane. And what happens for these curves is that on the null plane, if you let me call this coordinate x plus, it's a null coordinate. If you produce a boost, it will move x plus to lambda x plus with lambda positive. It's just a dilatation in the null plane, a boost. And then, if you think that you have a regularization that is invariant on the Lorentz transformation, your entropy of gamma will be equal to entropy of lambda gamma. Gamma, gamma is, so if these are transversal coordinates, the curve is described by gamma of these coordinates, y equal to x plus. But then you can put your lambda go to 0, and then S gamma is equal to S0. That is just a Rindler case. So all entropies are equal. And note that I haven't used anything about the entropy. I have only used the geometry. So if you can do the exercise of try to write a functional of curves on the null plane and try to write functionals that are different. So they have some structure. And you can see that all of these functionals give you the same number for all the curves. Because, of course, functionals that are invariant under Lorentz transformations. Because of this reason. And as all the entropies are equal, you have that the strong subadditivity is equal to 0. Just they cancel in the strong subadditivity. And this is very general and very geometric. And as I told, this do not depend on the functional being the entropy. It also holds for range entropies. It holds in other situations where you have a killing horizon, for example, in Kuiper space, where you have the invariant state and the killing symmetry. It also holds. So we have shown that for regions with boundary and null cone, for any quantum field theory, you have a strong subadditivity saturates, it's Markovian state. But now, if you have a conformal field theory, you can conformally transform the null plane to the null cone. So there is a conformal transformation between the null plane and a null cone. So you have strong subadditivity saturates for the conformal field theory, not for any quantum field theory. It saturates for this situation. So you take curves here.
Horacio?
Yes, finish the time, right?
Okay. Yeah.
Yeah. Okay. Perfect. Because I have already arrived to here. Then so here is strong subadditivity equal to 0 for a CFT. Okay.
You have 4 minutes left.
I have 4 minutes. I haven't heard that. Okay. So what does this tell you? That somehow the entropy as a function of gamma for a conformal field theory is a local functional of gamma on the null cone. because if you do strong subadditivity, it's just when you have the A, for example, the region A, it will depend on this point. When you have region B, it depends on this point. When you have the intersection, it will depend again on this point. And when you have the union, it will depend again on this point. If you have a functional that is local, automatically we satisfy strong subadditivity equal to 0. Well, but then we are in the position that we were wanting for, because we have some geometric shapes that are all curves on the null cone. For a CFT satisfies strong subadditivity equal to 0. So what we have to do now is just to apply this for theories that are non-conformal for a quantum field theory. So we have to apply strong subadditivity on the null cone. And automatically, this is the inequality will be 0 for the ultraviolet fixed point. Well, I think I will stop here, because otherwise it's not going to add much.
Okay, thank you very much. Okay, so we have time for questions.
Hi, sorry, I just had a question. Yeah, I was wondering, so you presented the saturation of strong subadditivity as some property of the state, but then it seemed like you had to choose your regions very specifically to saturate this. So
Yeah.
could you maybe sort of, is that more like a property of this choice of regions or of the actual state?
Of both together. So the saturation of strong subadditivity is a property of the state in the 1, 2, 3 regions, let's say. So you have to have this structure of the state. When you say that you have your state has this structure, is a state in 1, 2, 3, in the full region. Mm-hmm. Doesn't matter what happens outside, right? What happens outside doesn't matter. But in these 3 algebras, let's say, the algebra is a tensor product of 1, 2, and 3, you have to have this structure. So it's a property of both things, the state and the regions. So it doesn't happen, for example, for regions with boundary in the null plane for other states that are not a vacuum.
Okay.
No, it doesn't.
Great, thanks.
So it's a very particular situation that only because it's a saturation of strong subadditivity, so it's quite particular situation. It somehow tells something that is in a contrary direction of the Reversibility theorem. The Reversibility theorem tells you that you always somehow, you have 2 regions with some volume, you always have entanglement between them. And this tells you that if you have somehow the different lines on a null plane, the different lines on a null plane are unentangled to each other. This is precisely what happens for a free theory. In a free theory, you can describe the vacuum state reduced somehow to the null surface itself, and you have a tensor product of states for different lines. For an interacting theory, this is not really correct. It's a nice way to think about it, but it's not really correct mathematically, because there is no algebra reduced to the null plane itself. So the best way to say that is just the strong subadditivity saturates, and that's it.
Okay, great. So you have to, is that like in the free theory, you have to be able to localize it onto this smaller
Yeah,
surface,
exactly.
which you can do.
exactly.
Okay.
In the free theory, there are algebras that are localized in the null plane, and these are tensor products. There are no correlations between different null lines. But in a interacting theory, you cannot localize your algebras in the null plane.
Great. Thanks very much.
Actually, just to follow up on that, I mean, once you specify that it's localized in the null plane, then the non-interactivity just follows from causality, right? Because the null, there is no other way of
well,
influencing. Would that be a right way of thinking about it or not?
Well, the causality does not. So when you say there is entanglement between two things, you don't have causality because the algebras commute. So they are in tensor product, right? So the correlations can exist without causality, without commutations, right? So you can even for a free theory, you can excite a state of two particles that have correlations between this and this.
Good, I agree. Yes.
But it doesn't happen for the vacuum.
Okay, very good. Thank you. Okay, Shreya?
Yeah, I had a question about your argument for using the Reversibility theorem to show that there is entanglement between two general regions. So in that, so we wanted to show that that there are correlations between 1 and 3 in the original vacuum state, but then we acted on it with some operators in the region A. And then we show that after that, you can create a state which has an entangled pair between the two regions. So is that somehow assuming that this distillable entanglement is invariant under acting with operators in some local region or something like that?
No. The distillable entanglement means that if you have a bipartite system, let's call it here 1 and 3, the state is entangled in such a way that you acting with local operations and classical communication, you can obtain from this state something that is an entangled EPR pair, let's say, an entangled qubit, maximal entangled qubit, such a way that this distillable entanglement means that you can always, in these cases, you can extract EPR pairs from your state without interactions between the two laboratories, between 1 and 3. You just use local operations.
I see. Okay, so this is telling you that the original state had some distillable entanglement.
Yes, exactly. What it says that the original state, the vacuum between regions 1 and 3, has some distillable entanglement. Because of that, it cannot be an entangled state, and that implies that strong solubility cannot saturate.
Okay, thank you.
Better?
Yeah, in the strong subadditivity formula, there's 3 regions, A, B, and C. I'm a little confused what the 3 regions are on the cone. Is each region a
On the
curve
cone.
on the cone? Yeah, on the cone at the end.
Okay, so let me draw this. This is A, let's say.
Okay.
This is B. And then the intersection will be this region. So this is intersection. And the union will have you can describe your regions by just a boundary. So you have a region in space-time.
Okay, so it's a
boundary. Sorry?
It's a codimension 1 region. It's not a codimension 2 region. I was thinking it's just a line, but it's the tip of the cone as well.
So the boundary, so your diamond has dimension D, right? Is the full thing. the boundary of the diamond, the spatial boundary, the spatial boundary has dimension d-2. So this is a picture in 2+1 dimensions. So the boundary has dimension 1, are lines here, right?
Yeah, but the boundary isn't the region that you're considering. The region that you're considering is the boundary plus the tip of the cone, right?
The region that I'm considering is the full thing, is the boundary, the full null surface here.
Okay.
And there is also a past horizon, so there is also a past thing here. And the full thing with the volume inside is the region, is the diamond region,
Okay.
right? Has dimension d. But it is not necessary to think about the diamond that has a very complicated geometry. Is enough to consider the boundary, the d-2 dimensional boundary, to automatically and uniquely define the region. If you only consider this boundary, this automatically defines exactly what is the diamond.
Yeah.
You don't need anything else. You can also describe it by the null horizon, let's say. The null horizon, it also describes it uniquely, but all of these things will describe it uniquely.
Okay, that answers it.
Great. Any?
So strong subadditivity is equivalent to monotonicity of relative entropy. So I guess I'm curious whether anyone has actually like written down like a quantum channel corresponding to an RG flow.
Well, it's interesting, but maybe I can say something about that in the next lecture. But strong subadditivity, the problem here is that the strong subadditivity is monotonicity of mutual information, but we are interested in using it, something like this, 1, 2, 3. We are interested in using it when the mutual informations that you want to compute, so it's something like mutual information of 1, let me see, 1, 2 is smaller than mutual information of 1, 2, 3. So because of monotonicity. But both of them are divergent because they have the same boundary, you know. So the region 1 and region 2 are touching each other. If you do that for 3 balls, then monotonicity of mutual information is between finite things. But here are even if a strong subadditivity, so the full thing, if you have mutual information 1, 2 minus mutual information 1, 2, 3 is finite, it can be finite. These two things are divergent. So this is a problem in this sense that we would like to understand how to put these things in terms of relative entropy better or something like that. There are hints that something of what you say might be important in the sense that I will show tomorrow how somehow the irreversibility of Romanization Group is somehow related to the fact that you fail to reconstruct the state given some partial states in some geometric construction for the cases where the theory is non-conformal, where there is a Romanization group running, there is some failure of reconstruction of the state from its partial states. So there may be something related to that, but to my knowledge, nobody has clarified that.
Thank you.
Any other questions before we go to the informal part? Okay, so it's good time to stop the recording and thank Horacio again.